Good. So my name is Ager. I'm here to talk about Oilpan, which is a trace and garbage collector for Blink. And for my talk here, I'm going to live on the edge. And as you can see in my terminal here, I'm running an Oilpan build. So I'm actually printing out every time we have a garbage collection here. So I hope it doesn't crash. So this is the latest version of a Chromium build with Oilpan in it. So this has the entire CSS and Node hierarchy in the Oilpan heap and traced. So let's hope that works. Sounds good. Good. So Oilpan is a project to introduce a trace and garbage collector to Blink. And the goal of the Oilpan project is to make it easier to hack on Blink, because reference counting puts some restrictions on what you can do, and we can help with that with a trace and garbage collector. Also, we want to reduce the amount of leaks caused by reference cycles, and we want to improve security. And the way we usually improve security is that right now in the system, to break reference cycles, you use raw pointers. And if you forget to clear out some of those raw pointers, that'll be stale pointers, and you'll have serious security issues. And again, hopefully Oilpan will help here. So in this talk, I'm going to tell you a little bit about the reference counting issues where we're trying to help here. I'll tell you something about the Oilpan infrastructure itself, and then I'll spend some time talking about how to program Blink with Oilpan. Because there's some things that we're putting in the Blink programmers' hands that you guys will have to do when you program Blink with Oilpan. And we're going to help you as much as we can. And I'll also talk about how we're going to help people do the right thing for Oilpan. Good. So let's start out with reference counting. You all know this. You're Blink programmers. You live with this, right? So reference counting is an automatic memory management technique. You associate a counter with every object, and then you use these smart pointers called ref pointers to increment and decrement the count. And when the count reaches 0, that means that the last reference has been removed to the object, and the object is deallocated. And that has some classical issues. The main one is that if you have a reference cycle, then you can't reclaim that cycle, because the reference counts will never reach 0. If there's a cycle, the reference count will always be at least 1. Right. On the slide here, I say that cycles cannot be easily reclaimed. And by easily, I mean you could have a cycle detector that's basically running on the side, inspecting your structure, and finding cycles that are only keeping each other alive where you have no incoming references. We don't have that in Blink, and I don't think we should add it, because if you have to trace the object structure anyway, you should do a trace and garbage collector, and that's what we're doing. So the fact that we cannot reclaim cycles with ref pointers here leads to nasty things. It leads to the use of raw pointers to break cycles, and it leads to hacks otherwise to ensure that objects live and die together. Both of these things are hard to understand, and they're also really bad for security, in particular the raw pointers that can become stale. So, that's very small. Can you even see that? Anyway, I have a couple of examples here. So the first one is HTML media element has a list of text tracks, and that's represented as a text track list object. And these two objects should actually just live and die together. They should just be paired, and one shouldn't die before the other. The way you normally do that is they just strongly reference each other, right? But if you do that with reference pointers, then you have a tiny cycle here, and you'll never be able to reclaim this. So instead of doing that, we sort of make one of the objects the master object here. So we say that the HTML media element is the one sort of deciding here. It's the main guy, and he references. He has a ref pointer to the text track list. And then in order to break the cycle, we just have a raw pointer back. The problem with that is that the text track list is accessible from JavaScript. So it's perfectly possible for the text track list to outlive the HTML media element. If you just pick out the text track list from JavaScript and then detach the DOM tree, then you'll destruct the HTML media element, but you'll still have a reference to the text track list. And therefore, when the HTML media element dies, then in the destructor, you have to go to the text tracks list and clear out the owner pointer. Okay. So that's the kind of thing that you have to do. If you do not have ref pointers in both directions, then one of your objects can die before the other one, and you have to clear out these pointers, because otherwise you'll have stale pointers in your system, which would be really bad for security. And there's actually a little bug here that was fixed by Sigbjørn recently, which is that down here, where we get the execution context, there's no null check of the owner pointer. So when we have all these pointer clearings going on, there's a lot of null checks that we have to do, right? If the text track actually outlives the HTML media element here, that will be a null pointer. So this is a relatively benign null pointer crash. It's annoying, but it's relatively benign. If we had forgotten to clear out the pointer, it would have been really serious for security. Here's another example of how we're currently dealing with lifetimes in Blink. So in IndexedDB, there's a request and a cursor. And they're not supposed to die independently. So they have ref pointers to each other. And that's, of course, a problem because that'll leak, right? We can't get rid of that. Except that there's this great hack that says that in the request and also in the cursor, if you deref the request, you overwrite the deref operation. And then if the reference count becomes 1, not 0, but if it becomes 1, then you check your partner object and say, is your reference count also 1? And if it is, then you tear them both down at the same time, right? So that's cute, and it works, and these objects live and die together, but it's a case-by-case basis hack, right, to make it work. Another issue with reference counting is that it's just too expensive to do it right. So with reference counting, you should always be using a ref pointer, right? If you have a reference, you should increment the reference count. And when you don't have a reference anymore, that should decrement the reference count. That's not what we do, because it's just too expensive. Instead, we say, we cheat, right? We say, if someone else has a reference pointer, I probably don't need one, so I'll just pass around a raw pointer and operate on it. But then what happens if that reference pointer is actually cleared out? Well, then you lose, right? Then you have a raw pointer, the object gets deallocated, and you're using a stale pointer, which is really bad for security, again. Okay? So that leads to the pattern that I have on the slide here, where there's a method here that takes a raw node pointer, and then you put in a ref pointer here and say ref pointer node protect of node. And it's only there to make sure that the reference count is at least 1. No matter what the rest of this method is going to do, the reference count remains 1, so that you can use the node again at the end. Okay. So basically, that's only needed because we're cheating. Right? We're passing in a raw pointer here. That should not be allowed. That should be a ref pointer, because this is a reference. That needs to count. You're alive, I need you. We're not doing that, and we're not doing that for performance. And that's a very good reason. So I'm not pointing fingers again. That's the kind of things that you have to do to make reference counting perform. Okay, so contrasting that to a tracing garbage collector. A tracing garbage collector is also an automatic memory management technique. Instead of being based on how many references you have to an object, it's based on computing transitive reachability in an object graph, starting from a set of roots. And then anything that you can reach from those roots is alive, and you'll keep it around. And anything that you can't reach from those roots will be reused. So what that means is that cycles are not a problem, because if you have a cycle that is not reachable from your roots, well, then it's not reachable, and it'll be reused. So that means that for the structures that we saw before, where there's basically 2 objects that should be paired, that's perfectly fine. You'll just have a strong pointer in both directions, so you'll trace the structure. If you have a pointer to one of the objects, the other one will be kept alive, and they will live and die together. So these 2 objects, if one of them is reachable, the other one is too. And if none of them are reachable, they will both die in the same garbage collection cycle. That means that you don't have to clear out any pointers from one to the other. They're always connected, and they will die together. Okay. So no more hacks to actually represent cyclic data structures. And there's a lot of cyclic data structures in Blink. We just take the document structure is actually a strongly connected graph, most of it. But that's not the way it works right now. Actually, parts of that strongly connected graph can die on you now. And that's kind of funky. Good. So no more backpointer clearing, no more hacks to represent cyclic structures. And we don't need to do the cheating. And I'll talk more about that. But with a tracing garbage collector, one of the things that's in the root set is the stack. So every pointer that's on the stack will be found by the garbage collector and will be kept alive. So the protect pattern that we have right now will be gone, because using a raw pointer on the stack will no longer be cheating, because the garbage collector will know about those pointers and those objects will be kept alive. Good. So what are some of the issues with tracing? Well, first of all, in order to even be able to implement tracing, you need to have some infrastructure in place, because you need to know about all of the pointers into your heap. So you need to know about pointers from the stack into the heap. You need to know about pointers from objects that are not on the heap into the heap, and you need to know about pointers between heap objects. And that infrastructure is not there normally in a C++ code base. You can't just find the pointers for any given object at runtime. So that's what we've had to do for Oilpan, implement that kind of infrastructure. Another classical issue with tracing garbage collectors is that when you perform garbage collection, you go through all of the memory, basically. And that can lead to some pause times. And that's something that we're very aware of. Luckily, there are many techniques to avoiding those kind of big pause times too, but it's definitely something that you need to be aware of when doing a tracing garbage collector, and that's one of the things where we need to have better measurements, and we need to see that this will not become a problem before we ship the performance critical parts of Oilpan. I put a little question mark here because it's sort of reference counting is not without pause times either, because you get these deref storms in a reference counted world. So if you remove the last reference to a document and there are no other references to anything else in the tree, then you'll like do this deref storm and you'll deref every object individually. And that's also expensive, and the program will not continue until that's done. So there's also pause times with a reference counted system. Okay, but that is a concern when you have a tracing garbage collector pause time, and we need to make sure that that's good. Good. So that leads me to talking about the actual Oilpan infrastructure. Good. So there's a distinction here that I like to talk about a little bit. So there's a distinction between precise garbage collectors and conservative garbage collectors. A precise garbage collector is a garbage collector that knows everything about pointers. It knows exactly what is a pointer and what is not a pointer in the entire system. And that means that the garbage collector can keep alive only the objects to which you actually have a pointer in your system. Right? And then there's conservative garbage collectors who sort of try to determine what is pointers, but does not have precise information. So for instance, it could treat an integer like a pointer, even though it's actually not a pointer, and thereby keep some extra memory alive that it really shouldn't keep alive. Right? Oilpan is somewhere in between. So I call it a mostly precise garbage collector. And it's somewhere in between because we're conservative on the stack. So if you have a stack, we actually don't know what's a pointer on the stack. So we'll just look at every single word. We'll assume that that could be a pointer. We'll look at the value. And if that could point to one of our objects, we'll keep that object alive. Okay? That sounds bad. And it is. But Blink is an evented system. So we often get back to the event loop. When we're at the event loop, there's no stack. So most of the time, when we're at the event loop, we don't have a stack. Therefore, we don't need to do this conservative stack walking. And therefore, that part of the conservatism goes away. And that's the only part that's conservative about Oilpan. The rest of it, we have precise pointer information. So we have precise information about pointers from objects outside of the heap into the heap, and about pointers from heap objects to other heap objects. So the place we're conservative is on the stack, and that only happens in the rare case where we can't get back to the event loop to do our garbage collection. Okay, so Oilpan uses a simple mark sweep algorithm, and it's completely stopped the world. So we have a number of threads attached to the Oilpan infrastructure. They want to allocate objects in our heap. When we want to do a GC, we need to get all the threads to a safe point. A safe point is a point in time where all objects are initialized. They don't need to have their full structure ready yet, but they need to be initialized to a state where the garbage collector is okay with them. And that could be that some fields are null, or it could have the real pointer values. But it needs to be consistent. It needs to be in a state where the garbage collector can deal with it. So a safe point is a place where objects are initialized, and until you leave the safe point, nobody is going to mess with the object structure. So the object structure is stable. Okay? So once we get all threads to a place where they're willing to guarantee that they're not going to mess with the object structure, and before they mess with the object structure, they will block until you tell them that it's okay again, right? Then one of the threads will carry on. It will perform the transitive reachability computation, and it'll put a little mark on every single object that it can reach from the roots. Okay? Then we wake up all the threads. They will take their individual portion of the heap from the beginning to the end, and then they'll just step through all of the objects. For every single object, they'll look at the mark bit and say, did we set this little mark that says that this object is alive? If we did, then we'll keep the object around, clear out that mark bit, but leave the object around. And if the mark bit is not set, then we'll reuse the memory by putting it on a free list. Good. So what are the requirements so what do you need to know in order to implement mark sweep? Well, you need to have a size for every single object. So the sweeping phase just looks at all of the memory. So basically, it takes a void pointer to the beginning of the memory region. And then from there, it needs to be able to treat that as an object and check for a mark bit. And it needs to be able to move on to the next object. And it doesn't know anything about the type of the object. So there needs to be some way, based on just a raw pointer to a piece of memory, to say, I know there's an object here. What is your size? Is your mark bit set? So we need a mark bit. We need a size of the object. And then for tracing, we need to be able to find all pointers from a given heap object to all other heap objects, right? Because otherwise we can't do the transitive reachability computation. And all of these is sort of a problem when you're talking about a C++ code base, because Blink objects are just C++ objects, and we do not control anything about C++ objects. We use various different C++ compilers, and the C++ compilers are completely free to lay out objects any way they like, right? So we don't know about the size. If you just have a void pointer to an object and you don't know anything about the type, you can't just extract its size. We don't know where there's a free bit in a random object for the mark bit, and we certainly don't know where the pointer fields are in an object. So that's what we have to deal with Oilpan and provide the infrastructure where we can find these things. So how do we do that? Well, first of all, we allocate objects in our heap with a 2-word header. The size and the mark bit is in the first word, so that takes care of that. If you have a pointer to an object, you know that it has this header, so you can go back to the header and find the size, so that you can use for sweeping. You can also find the mark bit, because that's there too. Then the second word is some type information. I'll get back to that. There's a second word here. And then you have the C++ object. So right after the header, that's just a raw C++ object, the way that the C++ compiler decided to lay that out in memory for you. Okay. So that takes care of size and mark bit. The second bit here was being able to find pointers for a heap object to other heap objects. And there's just no reliable way to do that without involving the object itself. So that's what we're doing. We're letting C++ objects describe themselves to us. So as a Blink programmer, you will actually have to write the code that tells us about all the pointers that you have to other heap objects. Okay, so a little comment about this 2-word overhead here. Please remember that many of these objects are reference counted. So there's a counter that we're getting rid of. So that reduces the overhead a little bit here. The other thing is that the type info, the GC info pointer here, that's the same for every object of the same type. There are a lot of objects of the same type. The entire node hierarchy, for our purposes, has exactly the same type, namely node. And therefore, if we specialize heap pages on types, then we can get rid of that pointer, because it will be the same pointer for every single object on that page. So you can just move that pointer to the beginning of the page, and then the rest of the objects don't need to have it. And similarly, if there are very typical object sizes, you could even specialize in object sizes, put the mark bit somewhere else, and get rid of that overhead too. And other allocators have some overhead too. So it looks like a lot of overhead to have 2 words here. In reality, it's not, and we can bring it down a lot. Good. So let's talk a little bit about what it's like to program Blink with Oilpan. So there are 3 things that I like to talk about. The first one is, how do I get my objects allocated in the Oilpan heap? The second bit is implementing this trace method, telling the garbage collector about pointers from heap objects to other heap objects. And then the last thing that I want to talk about is dealing with finalization order issues. And what I mean by that is that with Oilpan, there are some changes to what you can do in destructors and what you cannot do. And you need to deal with that, and you need to know the tools for dealing with that. So I'll talk a little bit about that. Good. So getting objects allocated in the Oilpan heap. So right now, if you want to use ref pointers, you need to inherit from a base class called reference counted or ref counted. In the same way, if you want to get objects allocated in the Oilpan heap, you need to inherit from a base class called garbage collected. And there are actually two of them. There's garbage collected and there's garbage collected finalized. So if we take garbage collected finalized, it overrides new and delete. New allocates in our heap with a little header. Delete does absolutely nothing. Well, it has a release assert, but you should never call it, and it does nothing. Garbage collected finalized calls the destructor of your object when the garbage collector realizes that this object is no longer reachable. And that means that when the garbage collector finds it during sweeping, notices that the mark bit is not set, that's where it calls your destructor. Okay? Garbage collector does not do that. Garbage collector does not call your destructor. And that's for performance reasons, because that means that we could do some nice optimizations, because we don't actually have to look at the object. We just need to know that it's dead, and then there's nothing more we need to do. It's dead, and we can reuse the memory. So let's have a little example. So here's a class client rect. It is currently ref counted, and it's also script wrappable. Okay, so in order to move that from ref counting into the Oilpan heap, you just replace ref counted with garbage collected finalized. Okay. So why did I choose finalized here? Well, I did that because script wrappable has a destructor, and that does some work. It doesn't really matter what it does, but it does something, right? So if I do not call the destructor on client rect, then the script wrappable destructor will not run, and we will not run this code. So that sounds dangerous, right? Because what if I had chosen to just write garbage collected? Then that destructor would not be run, and this says something, do security-related pointer manipulation. That's probably important. We should probably do that, and now we won't. So the good news here is that that is very dangerous, and we're very aware that that just cannot happen. This is just not allowed, and therefore, as part of the Oilpan project, we have implemented a Clang plugin that will catch these kind of issues for you. So we will only allow you to use garbage collected if Clang can guarantee that your destructor is trivial, and Clang says that your destructor is trivial if it's generated by Clang and it's empty. So if you have any user-defined destructor, you cannot use garbage collected finalized, because then it's not safe, because that code won't be run. And it doesn't matter if the user-defined one is empty. If there is a user-defined one, you're not allowed to use garbage collected finalized.
You're not allowed to.
Oh, you're not allowed to use, sorry, you're not allowed to use garbage collected. You should use garbage collected finalized, because that's the one that calls the destructor. You're not allowed to use garbage collected. And here, if I use garbage collected, the Clang plugin will say class client rect requires finalization, and there's a note there that says that the base class script wrappable requires finalization. So okay, I require finalization because one of my base classes requires finalization. Okay, so this code will not compile if I do it wrong. Good. So implementing tracing. So for tracing, we have a root set, and then we need to trace through the object graph. Okay. So so there are a number of types of pointers that we need to find here. So the stack is part of the root set. So we need to be able to find pointers from the stack into the heap when we're not at the event loop. We need to be able to find pointers from non-heap objects into the heap. And then once we have these roots, that's sort of the initial set of pointers into our heap, we need to be able to find all of the pointers from heap objects to other heap objects. So pointers between objects. We have this special pointer type called member. And then you need to implement a little visitor pattern in your object. And the rule here is that for pointers to other objects, strong pointers to other objects, you need to use the member pointer type. And then you need to trace it in your trace method. Okay? So let's have a look at that. So this is probably a little bit too small for you to actually see, but what's here is a document. Document is a container node, and container node is a node. So if we move the entire node hierarchy to the Oilpan heap by making it inherit from garbage collected finalized, then this is in the Oilpan heap. We need to trace all the members. We need to tell the garbage collector about all pointers to other objects allocated in the Oilpan heap. Okay, so we move node to the heap. That means that we have to add a virtual trace method to node, and that should trace all of the members in node. Then container node has an override of that trace method, and document has an override of that trace method. So if you actually have a document, the trace method that you'll hit is the one in document because it's virtual. Now document here, I've added two members. So there is a pointer to a CSS style sheet, and there's a hash map from strings to HTML canvas elements. And if canvas elements are on the heap, CSS style sheets are on the heap, we need to trace these pointers. So we have heap versions of collections as well, and they also need to be traced, because that means if you have a heap collection, then the backing store is on the heap, and the heap collection itself knows how to trace the pointers that's inside of it. So if you have a heap collection as a member, you need to trace it, and then the system will take care of the rest for you. Okay, so for the document, the trace method is simply taking a visitor, and then it's calling trace on that visitor with the members as arguments. So these trace methods are very stylized. You have a number of pointers to other heap objects. You have them in members, and then in the trace method, you just call visitor arrow trace with every single member. And then you need to call the superclass trace method, because you need to trace the members of the superclass as well. Okay, so it's really stylized. So what you do here is you trace every single member, and then you call the superclass trace. And you do that in all of your classes. So again, this looks dangerous, right? Because what if you don't trace something? Well, that will lead to a dangling pointer, because if you don't trace something, then the garbage collector doesn't know about it. And if that was the only pointer to that object, the garbage collector will say, well, okay, it's not live. I haven't seen it, so it's not reachable, and therefore I can destruct it, and then you have a stale pointer. So again, yes, this looks dangerous, and here comes the Clang plugin, and it tells you that you forgot to call the superclass trace. So container node of derived class document requires tracing, and you haven't called it. So this won't compile. It also tells you that document has untraced fields that require tracing. And then it says untraced field M element sheet is defined right here, and you didn't trace it. I will not compile this code for you. You're doing it wrong. So there are some programming rules here, both when it comes to finalization and when it comes to tracing. And we've done our best to implement a Clang plugin that will not compile, that will not allow you to compile your code if you're doing it wrong. And that's because this is really critical, right? I mean, if we do not get the trace method right, then we're no better off than with the raw pointers in the ref counting case, right? Then we'll still get dangling pointers. So, is there a question down there? Yeah, so the question is why doesn't the plugin just generate that method? The answer to that is that it's sometimes a little bit more complicated when it comes to weakness, for instance. And also we don't use Clang on all platforms, so you can't use Clang to generate this one. We only use Clang on Linux right now, I guess. Mac also, yeah. But they're like Android uses GCC, and Windows uses Microsoft's compiler, and so we can't. Is the answer here. So what we've tried to do instead is make it really, really stylized. So it's always taking the visitor, calling trace on your fields, and then call the superclass one. And then at least it's very stylized, and we have the Clang plugin to help you if you're doing it wrong.
Looking to the future, if you did have Clang everywhere, what would you do ideally?
The question is, if we had Clang everywhere, what would I do ideally? I don't know, honestly, because I honestly don't know how to make the Clang generate this in a way where you don't get into like a giant mess with include cycles and all sorts of stuff. Like, where do you generate them? Where do you, like, how do you compile that? How do you make sure that you have the right includes and all of that? It might be possible, but it's not. It's honestly not something that we've thought a lot about, because that's not reality right now. So we can't do that. Yes.
Does the untraced field error only kick in when you just get the member wrapper? What if you have a raw pointer?
That's a good question. So the answer to that is that yes, right now, but that's because we're in transition. The end result should be that there should be no raw pointers. You should explicitly deal with pointers with Oilpan. That means there should be no raw pointers, there should be no references. A reference is just a pointer. So there should be no raw pointers, there should be no references. There should be members and weak members, basically. And the plugin is ready to do that, but we've disabled the check because while we're doing the transition, there are still some raw pointers that we haven't explicitly dealt with yet. They're sort of safe in the current state, and we haven't dealt with them yet. So the answer here is that long term, when we're getting ready to ship this, the Clang plugin will complain about a raw pointer to a garbage collected object, Therefore, you'll have to put it in a member or a weak member, and then if you forget to trace that, then the CLang plugin will complain about that, and therefore you're forced to put it in a member and you're forced to trace it. Good. That was one too far. So that was for pointers between heap objects. For pointers from non-heap objects to heap objects, we have this special pointer type called persistent. And persistent is just a pointer type that makes sure that this pointer becomes part of the root set for the garbage collector. So if you have a persistent, that registers that pointer with the garbage collector, and the garbage collector will always visit that one as long as that persistent is alive. So here's an example. In the current state, we haven't moved frame to the Oilpan heap. We have moved DOM window. And a frame has a pointer to a DOM window, so that has to be a persistent. And that means as long as the frame object is alive, there will be a persistent. That persistent will have registered the pointer with the garbage collector, and therefore if you get a garbage collection, that will be part of the root set, so the object will be marked and the trace method will be called. Okay, and then when the frame object dies, it will tear down the persistent, and that will unregister that pointer from the garbage collector. Okay, last thing here. Tracing pointers on the stack. Just use raw pointers for arguments and for local variables. Because we're conservative on the stack, when we have to be, so if we can get back to the event loop, we don't even have to look at the stack. But if we do have to look at the stack, we will find all of your pointers there. So just use raw pointers, pass it around. It's perfectly safe. You don't need to do any protection. It's perfectly safe to have a raw pointer that you're operating on. And then as part of what you're doing in that method, you end up clearing out the last member or the last persistent to that object. You will still have the pointer on the stack, and the garbage collector will find that and keep the object alive. So you don't have to use any kind of protect pointers here. We will find your pointers on the stack. Good. So that was about tracing. So the last thing that I want to dive into a little bit here is finalization order issues. So objects that have strong pointers to each other and are traced will live and die together. So if you have like pairs of objects that have pointers to each other, they will die in the same garbage collection round. However, there's absolutely no guarantee on which object will be destructed first. No guarantee whatsoever, and that's because we're just sweeping from one end of the heap to the other end, right? And then every single object that we find that does not have a mark bit set, we will call the destructor of that object at that point. And we don't know anything about like why is that there, right? So and not something else. So this is different from the current system because with the current system, a ref pointer guarantees a destruction order, right? So if you have a ref pointer from one object to another, then the first object has to die in order for the ref pointer to be torn down so that the second object can die. So that puts a finalization order on your objects. You don't have that with Oilpan. So objects die in any order if they're in the same group of objects. So what that means is that in your destructors, you can no longer touch other garbage collected objects because they could have already been destructed. Okay, and that's a big difference with Oilpan. However, it turns out that most of the time you actually don't have to. So most destructors in Blink right now deal with clearing out pointers because of raw back pointers. So there's usually like this block of code that says, clear out yourself, remove yourself from a set, clear out a pointer from that object to me, clear out this pointer. All of that can go away. So a lot of destructors just become empty. There are some cases where you're using actual weak pointers. So you want to have a pointer to another object, but you don't want to keep it alive. So basically, you want to operate on it as long as it's there, and when it's not, that's fine. That's a place where you commonly also use destructors, because the object that you're observing will basically have a list of everybody who's observing, whether or not it dies, and then it'll tell the objects that now I'm dead, right? But if those objects are also dead in the same cycle, you don't know if they've been destructed already. So you can no longer do that. So for that reason, Oilpan has support for actual weak pointers that are managed by the garbage collector. And let's talk a little bit about that. So member was the pointer type we had for strong pointers. We have a weak member that's for a pointer that you do not want to actually keep the target alive, but you want to know when the target is gone. So a weak member has the property that it will not keep the target alive. Instead, in the GC round where the target dies, that weak pointer will be set to 0 by the garbage collection system, not by the target object. Okay. So what does that look like? Well, here's like a lifetime observer thing with Oilpan. So you have an observee. You wanna know when an instance of that class dies. Okay. The observee doesn't need to know anything about the fact that it's being observed. So that's just an object. Okay. Then the observer down here has a weak member to an observee. That weak member has to be traced so that the garbage collector knows that it's there. And again, that's checked by the Clang plugin. And when you do that, then when the target dies, the observee member here will be zeroed out. And that means that you need to have these null checks, of course, because the pointer could be gone. But there's no destructor code involved here, as you can tell. No destructor code at all. So that is another common way of dealing with the finalization order issues. So usually there's a lot of pointer clearing that you can get rid of. The pointer clearing that you cannot get rid of because there's actual weakness involved, you should use our weak member support. And we also have support for weak collections. So you can put these weak members in collections as well. So if you have a weak member to something in a hash set, that means that if you get a garbage collection and some of these objects that are in the hash set dies, then they'll be removed from that hash set. So you will not have stale pointers in there. Okay. So just for a little bit of context here, with the current programming model here for Blink is basically that the observee here would need to know everybody observing it so that he can tell them that I'm now dead. And the I'm now dead happens in the destructor. So there's some destructor code there. And then the observer needs to register itself with the observee. And when he dies, if he dies before the observee, he needs to unregister himself over there. And then there's a clear method that sets the pointer to 0. So it's like 2 pages of code here just to figure out that some object died. And it's the responsibility of the dying object to tell everybody else that, hey guys, I died. So we're turning that a little bit around and making it a little bit more local. Good. So to sum up the finalization order issues, you cannot touch potentially dead objects in your destructor. That means that if you have a member to another object, you cannot touch it in your destructor. Usually it's easy to avoid. You should prefer strong pointer relationships. So if you have something that should just live and die together, please just use a strong pointer relationship. Make it cyclic. Make sure that these objects are in a group of objects that you should just live and die together. Then you don't need any of this pointer clearing stuff. If you want to only observe, use the weak pointers that we have in the system. Was there a question on it?
Yeah. When are weak pointers cleared? If there's a stack, what happens if I'm in the middle of a function?
Right. So so the question is, when are weak pointers cleared? What happens if I'm in the middle of a function? So if you're in the middle of a function and you have a pointer to that object on the stack, then it's not dead. And therefore, the weak pointer is not cleared. So it's only cleared when the pointer is determined by the garbage collector to be unreachable. At that point, you'll call the destructor of that object, and you'll also clear out all the pointers to that object. Similarly, if you have collections that you're iterating over, so if you have a collection of weak pointers, and you have an iterator, then it would be pretty bad that if you have an allocation during iteration, that could trigger a garbage collection. And it would be really bad if you start modifying the collection that you're iterating over, because our iterators do not support that, right? So that means that if you have an iterator, the Oilpan system will actually strongify all the pointers in your collection while you're iterating it. That means that none of those objects will die. None of the objects that those objects are pointing to will die in this garbage collection round. But they can die in the next one.
So what if my function just does null check against the member, and then later down it uses the member?
That's a very good point. You need to make sure that you extract it as a local variable, right? Or you null check after every time there could be a garbage collection, and that is non-trivial, right? So you need to make sure that you have it either on the stack or you do the null checks after something that could cause death of objects, and that is not trivial.
And isn't the compiler free to optimize that, like check register?
Yes, we do have we do flush out registers before we do the for conservative scanning. Yes. But yes, basically you need to do null checks, and you might need to do null checks more frequently if you just use the raw weak pointer. That is true. More questions, Eric?
Yeah, you gave me a ton of questions. So for his weak pointer question, can you just help him to
can't we use a type in accessing pointer members that you're forced to put them into a local?
Yes.
Something this is
Yeah, well, I mean, we could do that. I mean, one way of doing that is to just say that you can't. Basically, you can't access a weak member other than turning it into a pointer. But yeah.
Does the Clang plugin also support? Does it yell at me if I do something in my constructor?
Yes. Yes, it does. Right, and we also have ASAN integration. So that means that we actually poison memory that we've already dealt with. So in an ASAN build, you'll get a stack trace and say this destructor messed with some object that has already been destructed. Actually, in the beginning, so right now the ASAN integration is not perfect in the sense that we only poison objects that we have swept. We actually started out doing full poisoning of the entire heap, and then you unpoison one object, destruct it. And then if it touches any other heap allocated object, you die. Okay, so we can't do that right now. And the reason why we can't do that is that we're not done with the transition. So some of these patterns for for lifetime observation are actually still in there. And they're safe because one of the objects will die before the other one, and then he'll unregister himself, but that object hasn't been destructed yet. So there are some patterns that are still safe, and that where we would trip all over the place with that strategy. But that's where we want to be. We want to be at a place where the ASAN build with Oilpan will poison everything. It will unpoison one object, destruct it, and then you're sure that it doesn't touch any other object, and then you'll poison it again. Move on to the next object. Yeah. Dan.
Yeah. So finalization is kind of a class. Is that a transitional place to and like we call back monolith for held resources, or is it something which
Right, so the question here is that finalization is typically a very bad idea in garbage collected systems, and this is something that we want to just try to get rid of completely and use some reprocessing schemes. That would be great. Right now, there's a lot of finalized objects, and to be absolutely honest, I don't know how far we can go with not having finalized objects. There's definitely a lot of things that we'd have to do in order to not have to call destructors of objects. So one classical example here is that we have strings. Some of those strings are atomic strings ref string impulse, atomic string impulse, and atomic string impulse are canonicalized via a thread local table. So basically, as soon as you have a string, you need to call the destructor because the string needs to be destructed because it might need to pull itself out of a thread local table. So there's a lot of things that we would have to deal with before we can say you don't have to finalize any objects at all. So I don't know what my personal answer is yes, I want to get rid of all of the finalizers because that would be great and they'll perform better. Whether that's realistic or not, I don't know, and it's definitely a bunch of work that we want to do, but it might take quite a while to get there. Yes, Peter.
So right now we've got Oilpan bots for Windows, Mac, and Linux, but not for Android. While Android is a platform where we know that thread counting is especially expensive, and other atomic operations are just generally more expensive as well.
Yes.
What are we doing to fix that?
Yes. So the question is, you have Oilpan bots for desktop systems, but you don't have it for Android. And that's true, and we're working hard on fixing that. So the particular thing that we're doing is we're setting up perf bots, which we also have for Oilpan on the desktop systems, and we have the hardware. So now it's just a matter of getting it set up. So we're actively working on getting that so we can track our performance, and that's going to be critical, of course, for the evaluation of the system when we're at a state where we think we're ready to actually ship some of the bigger parts. We need to do that evaluation, and we're doing the steps to get there. It's taking a little bit longer than it should, but it's underway.
If you need any kind of help, we're right here on London. Feel free to reach.
Cool, that's good. Thank you. Yes.
Why did they trace a weak? Does it mean it just takes forever? Why would it?
So the question is, why do I trace a weak member? Yeah. So that's just to let the garbage collector know that it's there. No. It's just that's just saying it's the way of telling the garbage collector that it's there. So it might be a little bit misleading to call it trace, but again, we just want to have this stylized trace method where you trace all of your members, and that includes the weak one too. But it is a little bit misleading that calling trace on a weak member does not actually trace it. It doesn't mark it. It doesn't trace it. It just means that here's a cell that if what it's pointing to becomes dead in this garbage collection round, you should clear it out. Yeah. Good. I should move on here. I think we're basically out of time. So I'll do a really quick status update here. So we're shipping the first modules with Oilpan in Chrome 36. That's a little bit of a trade-off because we don't have the full performance picture, as Peter points out over here. We don't have the Android performance numbers for the current version of the system. And that's, of course, bad. On the other hand, we know that some of these modules are not performance critical, and we're trying to strike a balance here. We want to get some input on the stability of the system without risking shipping something that will regress massively. And the trade-off that we've hit here is let's take some of the modules and ship those. Those are not performance critical, and let's get some input on the stability of the system doing that. And that also means that we take on the responsibility that if it doesn't fly, if we cannot get the performance good enough, well, then we will have to reintroduce reference counting to those modules. So that's the way it works. Good. CSS and Node hierarchies are well underway, and we're using these transition types, which are really, I really apologize. It's horrible, and we know it. So basically, you have types like it might be a raw pointer, and it might also be a member, maybe, and that's not very nice. So our types have this will be in the middle. So you have like a raw pointer will be member, and that means that when you're compiling with the current normal set of compile time flags, it's a raw pointer. And if you're compiling with enable Oilpan 1, it's a member. And that means that all of this code, basically, you have two systems in one code base here, compiled by a compile time flag. So when you're reading this, there's basically two versions of the code that you have to read at the same time. And it's really nasty. It is the best way that we have found to do an integration of Oilpan without basically shipping every intermediate step, and without continuing to live on a branch where we would get into a state where we could never ever ship any of this. So we apologize for them, but they're needed. So bear with us. Right, we're well underway. So the CSS hierarchy is mostly moved to the Oilpan heap. We've got the node hierarchy in progress now. We've made it completely independent of reference counting and fully traced. We haven't yet removed all of the ref pointers. We're in this weird transition state, and we're working hard on getting rid of all of the reference pointers and explicitly dealing with all raw pointers and all references in the entire node and CSS hierarchy. Once we've done that, and we're expecting to finish that at the end of this quarter, that's the time where we need to do a thorough performance evaluation and see if we're ready performance-wise to ship this for Node and CSS. And then there'll be, be some release engineering that we'll have to do there to make sure that stability is also in place before we ship. So there's going to be quite a bit of work involved in actually shipping this. But we're getting close to the point where we can actually get those performance numbers that we all want to have and start optimizing for the cases where it doesn't look too good. Good. So I might actually skip this because we're over time. So if you want to know about performance, just ask, and I'll talk about it. On the experimental branch, it looks good. Things have changed. We didn't have Android performance numbers on the branch, and we need to get those. So back to the question on the panel, do we still have something to prove? Yes, we need to prove that we're not going to regress stuff. We need to prove that our garbage collection pause times are not so bad that we cause jank all over the place. Right. So that's what we'll start doing over the next quarters. Over the next quarter. Good. Here's the team. We're all here, and as you can see, the team actually also includes a member from Opera, which is great. So this is a cross-company effort as well. Good. Any more questions? We already had some. Yes.
When does the GC occur? Is that like tied to the scheduler at all, to affecting animations and such?
That's a good question. So the question is, when does GCs occur? Is it tied to a scheduler to avoid hitting in the middle of animations and stuff like that? The answer is no, not right now. So right now, the heuristics are pretty simple. It's simply a matter of how much have you allocated since the last time you GC'd. And then you do not do the garbage collection at the point where you allocate the object that pushes you over that edge. Instead, you set a flag and say, when you get back to the event loop, please perform a garbage collection. because when you're back at the event loop, we can do precise garbage collection. And then there's another heuristic that says if you allocate a lot more on top of that, then oh shit, we're not getting back to the event loop, so you need to do the conservative one. So that's how it works now. But it's a great question because I imagine that a lot of the issues that we can get into here with exactly like stopping the world and doing something bad in the middle of an animation could be dealt with if we hooked up with some sort of scheduling mechanism that I don't think is in place yet, but that there's talk about having. So I'm really, really interested in that work, and because I think we can use that, and I think it'll be critical for us. Jochen. Yes, sorry, yes. Right, exactly. So what Jochen is saying here is that show model dialog is one of the nasty cases where you're actually running a nested event loop. And that means that as long as you're running inside of a show model dialog, there will always be pointers on the stack, and you will always do these conservative garbage collections that we don't want to. So it will always be the case that no, you don't get back to the bottom event loop where you have no stack, and therefore you'll always be in this mode where you like trigger the oh damn it, we're not getting back to the event loop, we have to do a conservative GC. And yes, that is absolutely true. Nice question. Thank you, Jochen. Then I can talk about that too. So the question is, how do you make sure that you get everybody to a safe point? In a worker, for instance, you could have, it's perfectly fine to have a worker that does computation that takes 5, 10, 15 minutes in JavaScript, and then it returns to you with a result. And that's absolutely fine, because V8 has this nice interruption mechanism that we put in there. And we can use that. So that's what we're doing. So basically, when we ask threads to reach a safe point, we ask V8 to interrupt itself. And then and we use the existing interrupt mechanism in V8. It's been there forever, and it's going to stay. And we're using that. So basically, at the next either method call in JavaScript or the next back edge of a loop, V8 will stop, and it will not continue until we tell it to continue. And at that point, we know we're at a safe point, because if you're in JavaScript code, you're not modifying the DOM when you're in the JavaScript engine. So if you can stop there, then you're at a safe point. So you don't have to get to an explicit safe point. It's perfectly fine if you're running JavaScript code. And actually, it would be fine to just perform a garbage collection while you're running the JavaScript code, and then just block you when you enter Blink again. However, that's a little bit expensive, because then you need to have checks on entry and exit from V8 and into the DOM. So that's why we're using the interruption mechanism instead, because that's a lot cheaper. You don't have to do checks on every entry and exit from V8. Oh, that's a good question. I don't know the answer to that. So the question is, if you have the inspector open, does that largely affect the garbage collection times? Is that right, Jochen? Was that the question? Oh, so the inspector will freeze the main message loop and run other ones? I honestly didn't know about that case, so we'll have to investigate that. Thanks for bringing it up, Jochen. I don't know the answer to that. I honestly don't know. So we'll have to investigate that. I'd be happy if you'd send me a pointer, Jochen, or I can talk to Pavel about that. We need to talk. It sounds good. Well, that sounds good. I don't think it's not a problem that you're using the same mechanism for the debugger. That's perfectly fine. But yes, I'll reach out to Pavel and we'll talk about this, and we will find a solution. So thanks for bringing it up, Jochen. I didn't know about that case. Thank you.